So experiment 1, determination of the energy of activation of a reaction. So energy of activation is designated as EA. This is energy of activation. According to Arrhenius, Svante Arrhenius, he proposed a formula that we are using, or we're going to be using in this experiment. And from his observation of what is called the rate constant against temperature, he was able to deduce that K, which is the rate constant, equal A exponential, then you have minus EA over RT. So we'll have this expression as proposed by Arrhenius. So in this expression, K is the rate constant, and then this is an exponential factor A, and that is activation energy. This is the molar gas constant R, 8.314 joule mole per Kelvin. So we have the absolute temperature. Okay, now in this expression, by taking the natural log of both sides, you can take ln K. This is going to be ln A. This exponential sign is going to go off, so I'm going to have actually just this one. So I'm going to have minus EA over RT plus this one. This is ln A, the Arrhenius equation. So this is what we're having, and as you can see, it's quite explanatory, because Arrhenius found out that you can rewrite this thing in this form by saying ln K equals minus EA over R multiplied by, this is 1 over T, okay, then plus ln A. So this is what we'll have, you can see here. So Arrhenius discovered that a plot of ln K on the y-axis against 1 over T on the x-axis will give you a slope that is equal to minus EA over R with an intercept as ln A, okay? And it's a straight line because you can see this equation is likened to y equals mx plus c, which is equation of a straight line, where a plot of y against x, a plot of ln K against 1 over T is m, which is the slope, and this m equal to this m minus EA over R, while c intercept is ln A. So if that looks like this, so here is ln A. Yeah, let me just call ln A. Excuse me. So we have ln A. So we have a graph 1 over T, in the sense that you're gonna have a graph that looks like this. So the intercept on the y-axis is going to be, sorry, I think I made a mistake somewhere. This is ln K, sorry, this is ln K. So the intercept is going to be ln A, you can see. So your slope will be equal to minus EA over R, like that. So this is what you're going to get. So from the slope, you can be able to get the activation energy. So if your slope, you got, let's say you got 4 as slope, so your 4 is going to be minus EA over R, which is the molar gas constant, which is 8.314. I'm not actually using the units here anyways. So you might even get a negative slope, or whichever slope you get. So you make EA the subject, cross multiply, you get your EA, the activation energy, and the unit is joule mole per Kelvin. Okay, this is the unit for activation energy. So with this, you'll be able to get the activation energy. Let's relate our background knowledge of Arrhenius equation to the experiments we have at hand, and then we'll be given 2 reagents. We'll be given potassium permanganate. This is potassium permanganate, okay? Then you're going to be given oxalic acid, okay? Ethanediolate. So let's just have it H2C2O4, okay? This is oxalic acid, and that's potassium permanganate. Okay, and we know that potassium permanganate is colored purple. So if you look at your manual, there's a balanced equation there where you get to see that the permanganate ion is undergoing reduction to manganese 2 ion. The oxidation state of manganese here is +7. So we are having a +7 to +2. This is a reduction, right? How did I get +7? Just manganese X plus 4, oxygen is -2, equal to -1. No, here is -1, okay? So X, this is -8, equals to -1. So X will be equal to -1 plus 8, which is +7. So this is how we got this. So there's a reduction, meaning that from +7, the purple color, to +2, it decolorizes. So the purple color decolorizes, the purple color disappears. So there's going to be a disappearance. And now this is the basis for this experiment. So you'll be given burex and you'll be taking 10 ml portions of both reagents, 10 ml of oxalic acid. So you take 10 ml of this and you take 10 ml of potassium permanganate, right? So you're going to heat them. Just put the separate test tubes in a beaker or whichever is provided for you that has been warmed at 50 degrees Celsius. Then you have a thermometer to be sure it's at 50. So you get to warm it to 50, let's say the 2 test tubes, one for oxalic acid and one for potassium permanganate. And why are you heating? You're heating in order to increase the kinetic energy of the molecules present in this reactant species, because temperature has an effect. It's a factor that affects the rate of chemical reaction. So it promotes that. So we want to, increase the average kinetic energy of the molecules in order for them to undergo effective collision. So, and activation energy has to be overcome. And bear in mind, in a case where activation energy is very little, the reaction tends to occur fast. But if the activation energy is very large, so that means the barrier is too much, so the reaction proceeds slower. So when you've heated these two sufficiently at 50, all you're going to do is going to pour into the other. You take this, pour into it. Immediately you're pouring into it, you are timing it, okay? You're timing it. This is at 50. Now you're going to have a table like this. You're going to have a table that looks like this. Let's say CSP number 1 at temperature 50. Okay, you have a time. Now, depending, you can also have T1, T2. You can repeat same observation recording at 50 2 times in order to get a better value, an average. So, but in this case, I'm going with just one run. So, let's say at 50, the decolorization occurred as, say, 20 seconds. This is time. This is degrees Celsius here. Okay, and then let's say 60, maybe the reaction occurred at, let's say, 18 seconds. And for you to be able to know, remember, potassium permanganate is purple, it gets decolorized. So the disappearance of the purple color, you stop the stopwatch, note the time. So that's how you get these times. So you have 70, if you have 70, then you have 80, like that. I'm trying to just give something that could be obtainable, not for a fact, okay? It might not be decreasing like this, it might not be, so it might be increasing. So based on your observation, you should get to see the trend. So I'm using this as an example, and in this example, I'm trying to see maybe probably it's going to be reducing, but definitely that is the way it's supposed to be, okay? Because increase in temperature allows for effective collisions. That means the reactions will occur at a very short pace time. So if increasing the temperature, the time required for that reaction will be much lesser because the molecules, the average kinetic energy of the reactant species, oxalic acid and potassium permanganate, is actually very much effective to lead to the formation of products. That is the decolorization of the potassium permanganate. So you have this, okay? Then you are expected to have a column for um, 1 over T, but bear in mind you have to convert this to Kelvin, okay? Convert these values to Kelvin. So 50 plus 273, whatever it gives you, is going to be here. Then you take the inverse. So the unit here is K inverse. Okay, you're going to have this inverse, okay, right? So now after having the inverse, you're going to have log 1 over T. So inverse of this, take the log, you have it on this other column. So you're going to have log 1 over T, okay? So log 1 over T is going to be here. So all your values here. Now you're expected to plot a graph of log 1 over T. So if you have log 1 over T against 1, this is time, right? Against temperature, inverse of temperature. So you're expected to have a graph that looks like this. Yeah. Now, why should the graph look like this? Why do you think it should look like this? Because as the temperature is increasing, let's say 50, 60, as the temperature is increasing, the time required for the reaction is supposed to be reducing. So as this, let's say here is 20, so we have 15 like that and all of that, but we have to take the log of this, so it could be around 0 point something. So as these values are reducing, okay, the temperature is increasing, telling you that temperature increases the rate of reaction, reducing the amount of time required for that reaction to occur. So now this intercept very important. So but slope, don't forget, slope is minus EA over R, okay? So this is how you get your slope, activation energy from the slope. Now if you remember, we stated earlier that ln K, right, is equal to minus EA over R, right, plus ln A, if you remember. Now this is 1 over T, right? Yeah. So in this case, we are plotting a graph of, you can see here, this ln K is this one, log 1 over T, which you see here. I've written before, you can see this is log 1 over T. So that is like into ln K here. Then minus EA over R is the slope. Now you can see this is the slope of this graph is minus EA over R. Then you have 1 over T, this is 1 over T. That means the intercept here is your ln A. So we're going to have whatever value that is here is ln A. This can help you in some other calculations, okay? So this is how basically you get to plot the graph of this experiment and then to determine the activation energy. You can actually get to know the order of the reaction because the graph we get to derive from our set of observations from your tables, and you get to have that straight line graph tells you that the reaction is that of first order. Why? Because the rate of reaction is um, dependent on the concentration of one of the reacting species. So it's dependent on one of the reacting species. The rate of reaction is dependent on, in this case, the disappearance of the purple color of the potassium permanganate. So we know that rate of reaction is directly proportional to concentration of the reacting species. So now, and we can say that rate is equal to, we introduce a rate constant K for A. Now, let's take this A to be potassium permanganate, the permanganate ion. So now this we can say as rates of reaction is changing concentration over time. So, and in that case, I'm going to have a negative sign, changing concentration. I'm only saying that there's a disappearance, this minus sign, disappearance of the purple color of the potassium permanganate with time. Okay, so I'm going to have the T. This is that. So it's going to be equal to Ka of the potassium permanganate. All right. Now, what I'm going to do is I'm going to rearrange. I'm going to take this A here. I'm going to take the T over there. So I'm going to have this expression. Okay. A, bring it A, this goes there. I'm going to have KDT. So I'm going to have this expression, right? So the next thing I'm going to do is, because the process is exponential at some certain time, so we're going to take the integral of both sides. So I'm going to have something like this, right? I'm going to have that. So when I do this, I'm going to have this is going to be natural log of ln A at a given time t. All right, this one, this here, I'm going to have ln at over a0, the limits, okay, sorry, it's supposed to be written like this, equal to, if you integrate this, you got kt, okay, minus kt, this minus sign over there. So we have this expression, and according to log rule, when you see this expression, when you see log x over y is equivalent to saying log x minus log y. Okay, so with that, bearing that in mind, I'm going to do that here. I'm going to have ln at minus ln a0 times 0 equal to minus kt. So I'm going to have this, okay, equal to minus kt. So once we've gotten this, you can still write this to be ln at equal to minus kt plus ln a0. This boils down to the fact that I'm trying to show you that this is also a linear equation, because this is same thing as y equals mx plus c, where c is ln a. If you remember, then this is x, this is t. When you plot a graph of ln a against t, your minus k is your slope. So in this case, for a first order reaction, ln a t against time, we have a graph like this where the slope is minus k. Slope equals to minus k. This is just for background knowledge of first order reactions. From your table, you should be able to also be able to calculate the activation energy, still using the Arrhenius equation again. Okay, so we can rewrite the Arrhenius equation, which says ln K2 over K1 is equal to minus EA over R open bracket 1 over T1 minus 1 over T2. Okay, right this. So in our own case, we can make use of, or if you want to go to the extent of finding K1, K2 and the rest of it. But in this case, we're going to be having ln T2 over T1. Okay, so you choose portions that are more. This equals to minus EA over R. So at that particular times, you're choosing that actually a little constant, not so much deviations from them. You can just use this value. So at T2 from your table, okay, there should be a corresponding T2 temperature. Okay, at T1 from your table, there should be a corresponding T1 temperature. So you have 1 over in Kelvin. Okay, so you have 1 over T1 minus 1 over T2. So with that, you'll be able to take the lane of the division of this. Then you should be able to substitute your values. This is a constant, to find your EA and relate it with your graph, the one you plotted earlier. And that is all about experiment 1.